Thank you very much. As you can see, the title of this talk is Good Ideas That We Forgot. And what I've tried to do is go back to perhaps 1960s, the 70s, and look through ideas that we've had and forgotten about. Because there were a lot of really good ideas in the past. And why do I want to do that? Well, I have certain goals. I want to remind you of some of these ideas. I'm not saying that everybody in the audience has forgotten these ideas, but maybe people who've been programming for 40 or 50 years, they'll know this stuff. But if you haven't been programming for 40 years, I mean, how many people have been programming for 50 years? So it might be that you've forgotten some of the ideas that were around 55 years ago, and there might be some good ideas there. So I want to, how about 40 years? 30 years? 20 years? 10 years? Less than 10 years? Right, okay. You've got a lot to learn. When I was a student, I was learning physics, and there was this old guy, he was really ancient, he was over 60 when I was a student, and he was teaching quantum mechanics, and he said, I don't understand how you can learn quantum mechanics in a year, because it's taken me 50 years to learn this stuff, and it was really tough, and the new ideas just came slowly, so I had time to assimilate them. And that's 50 years later, 45 years later, I'm standing here thinking to myself, goodness, you know, there's an awful lot of stuff today. And so if I was starting computing, what would I need to learn? There's an awful lot of stuff. Yeah. When I started programming, there wasn't an awful lot of stuff. There was, you could choose between Fortran and COBOL. And you could choose between paper tape and punch cards. And you could, I won't tell you. But it was different, right? And things are different now. So now, if you've got to choose a programming language, they're like, I don't know, 1,000 programming languages to choose from. Well, that's easy, isn't it? And of those, there's 20 that are crying, yeah, we're great, we're better than all the other programming languages. And of course, you don't have time to deepen the subject. You don't have time to, you can only see the advertising stuff. You don't have time to look at them in detail. And so you choose one of them, and you don't know, you don't know what to learn. So what I wanted to do was try and summarize what I thought you should learn, actually, and get that down to some small lists and what ideas are important. Some ideas are more important than others. How do I go about this? Well, actually it all started, I was interviewing Alan Kay. It was a great privilege to meet my great hero, the man who coined the term object-oriented programming. I thought, well, I asked Alan Kay. And I thought, I'll ask him, what's the good stuff we've forgotten about? And he started talking, and he said all these things, and I thought, yes, I could turn this into a talk. So I started asking people, and then I tweeted, I thought, oh, Linda Tuple spaces, and things like that. Everybody knows about it. Who knows about Linda Tuple spaces? Nobody? Oh, that's wonderful. That's absolutely brilliant. Well, you will after this talk. And I got a lot of answers. So I thought I'll collect these answers into lists, and I'll put them in lists. Collecting lists, that's really easy. And then, well, the trouble with lists is there's too many things in the list, so you have to throw things out of the lists to make them short. And that is very, very difficult. There's a book list here. Now, if you're at college, and your professor gives you a book list with 15 books, they know you're not going to read 15 books, but they can say, well, I'm a good professor, I've told you all these 15 books, but if you don't read them all, that's your fault, not mine. But if they cut it down to one book and tell you to read one book, then they are taking responsibility for that. Because if I suggest that you read one book, you might actually read it. And I will suggest, actually I suggest 3 books, this is terrible, but there's one book you should read. And if you don't like it, well, it's my personal point of view. You might not like it, but I loved it, it was great. Right, so, whoa! What did I do? I pressed the wrong button. Bloody computers. Play. Whew, right. What? No. Back. Forward. What? The slides changed. I think I asked, does anybody understand how a computer works? Right. Before I do this, I wanted to write down some principles that I thought were important. Because we'll use those principles to evaluate the other things I'm going to look at. Right, so here are some principles. Principle number 1 is called observational equivalence. In it says, we can define it, it says, 2 systems are equivalent if they cannot be distinguished on the basis of their observable inputs and outputs. And that means we can make the world up out of black boxes, we send stuff into them, stuff comes out, and if we cannot observe any difference, then our black boxes are equivalent. There's a lot of implied things there. That means we can change the language inside our black boxes. We can change the implementation without changing the system as a whole. And it implies we need several different languages. We need a language to describe the inputs and the outputs, maybe a type system or something like that. We need a language on the inside of the black boxes to describe the computations, and we need to describe how the black boxes are connected together. We mustn't forget these things. Now, most of the time, we think that we only need one programming language, and that's the language used inside the black box. What about the language to describe the things going inside and outside? Well, we don't really have good ways to do that. You can use JSON and XML and things like that, but they're rubbish. They don't really tell you what's going on. And they don't tell you what the sequencing of events are. This is state-of-the-art stuff. There are systems called session types, which allow you to say the sequence of operations. So session types is a hot topic in research, but it's beginning. I mean, it hasn't really got anywhere. Well, there are no session type theorists here, I hope. No, okay, right. Right. If I said that in ICFP, they'll kill me after that session. The second principle is isolation. 2 systems are isolated if what happens in one system cannot influence what happens in the second system. This is a very important principle. Who's got a computer? You've got a computer. Can I have you? I'd like to ask somebody from the audience, could they come up and I will smash their computer with a sledgehammer?
Do that in 3 months. I'm going to get a new computer.
Sorry?
Can you do that in 3 months? I'm going to get a new computer.
Oh, okay, right, yeah. Actually, I should do this as a demo. You need 2 computers. You run a program on one computer, then you smash it with a sledgehammer, and you show that the second computer still works. That's called isolation. and actually, it's a property of the physical world. If I take this stool, if I take this chair and destroy it, nothing happens to the other chair. It's great. Does that happen in your software? Got 2 objects in a system, the other one crashes. No. Programming language should automatically obey the principle of isolation. The third principle, composition. Things are composable if they can be combined in such a way that the combination behaves in a similar manner to any one of the individual components. That means we can take things and we have a basic understanding of how they work, and we chain them all together, and this compounded thing behaves like one of the individual things. That's called composition. And composition works differently in different programming languages. But the things we build must be composable. Right. So if you look at things like apps on an iPhone or on an iPad, are they composable? No. They're isolated. They can't talk to you. You can't script them. You can't do anything with them. You're locked in a prison. And you can't do anything about it. It's terrible. Horrible. Awful. Causality. I used to be a physicist. Effect follows cause. If things are isolated, if we've got one thing here and another thing there, then the only way that they can influence each other is by sending messages to each other. These messages travel at maybe the speed of light. This is physics. Okay? But until the message has been received, the thing that's receiving the message cannot do anything. That's called causality. So if A sends a message to B, B cannot do anything until it's received the message. And of course, A doesn't know if B has received the message. I never know, in a distributed system, I never know how remote things are. I know how they were in the past. Let's remember that. Physics. I had one with several physical books. For a computation to take place, all the data and the program must be at the same point in space-time. Otherwise you can't perform the computation. So you can move the data, or you can move the program. And what we typically do is we move the data. We don't move the program. That's why we set up the programs on a server and we move the data to the server. A bit silly, really, because in doing so we expose our data to the NSA and all the security people and Facebook and Apple and Google and everybody else, and everybody who decided GDPR requests. And once we've sent our data out, we've lost control. And anyway, the data's probably much bigger than the wife, so yeah, send me the program, I'll keep my data private. Right. And violating this law, when you're doing, for example, web programming, has strange consequences. If you were writing a web application in JavaScript, and you've got all the data you need, but not all the data, wait a moment, at some point in the computation, you say, oh dear, I haven't got all the data I need, I've got to go and ask a server. You send a message to the server, and then all sorts of things can go wrong. The server might not answer, and then you don't know if it's not answered or if the system's crashed. And you invent stupid things like futures and promises and all sorts of daft stuff. And it's difficult, because you've broken some laws of physics. Why is it difficult to program like that? Because you've broken the law of physics. You haven't got all the data in the client, you've got some of the data in the client and the rest of the data on the server, and you've broken the fundamental law of physics. That's why it's difficult. If you remember, you can use a wonderful programming language called PHP. Because you generate all the page in one place, where the database is, and then you send it to the client. And the client's stupid and doesn't do anything. And now they'll all be tweeting, say, Joe loves PHP. For the right reasons, not the wrong, I mean, it's not functional or anything. It's good, right. So violating any one of these principles will lead you to a brittle system. Your system might work for a while, but when one of these principles is violated, it'll sort of hit you in the face. And it's very difficult to understand what's gone wrong, because most of the time it'll work, and then it'll go wrong. So following these principles has many benefits. Isolation, it just kind of gives you fault tolerant scalability and security, all for free. You don't have to do anything. If two systems are isolated, hacking into one system won't affect the second system. If two systems are isolated, if one of them crashes, the other one's not going to crash. It's fine. Exercise. Think about it. What benefits come from obeying the other principles? You can think about that. Right. Part 2. Things to learn which you might have forgotten about or didn't know about in the beginning. So I managed to boil this down to 80 things. 2 papers you've got to read, 4 old tools you've got to learn, and 3 you go, 80? Well, the last time I gave it, this talk is evolving, so the last time I gave it, which is a couple of 3 weeks ago in Chicago, I tried to tell them all these 80 things and hopelessly ran out of time, so I've junked most of them. So if you see the video from Chicago, if you want to see the full 80, it's there. Right, okay. So here's a quick version, and I'm going to go over this quickly because I really want to get to this and forgot stuff. Here are 2 great papers you should read. They're fantastic. Tweet. Right. Here's 4 things you should learn: Emacs, Bash, Make, and Shell. I gave a tutorial. So how many people know? Oh, I'd ask here. How many people use Make? Oh, thank the Lord for that. How many people don't use Make? Oh dear. Sorry. I'd really like to ask you over coffee. Why do you use a different build tool for every programming language under the sun? It just doesn't make sense. You learn Make once, and you can use it for everything. Right. Enough said. 3 books you should read. Algorithms they describe. If you're only going to read one book and it's about computer science, read this book. It's by Nicholas Viet. And it describes in detail the P-code machine. Now the P-code machine is the precursor of the .NET virtual machine and the JVM virtual machine. If you want to understand how to make a virtual machine for a programming language, read that book. Complete detail. There's a little P-code machine for a language called PL0. It's very, very understandable. And a complete description of how to build an LR1 parser and everything. Wonderful book. Then there's, maybe we don't just do programming, we do project management. And then, you should read The Mythical Man Month. Who's read The Mythical Man Month? Oh, that's good. So, there's some notable takeaways from The Mythical Man Month. As Brooks points out, you want to have a baby in a month, get 9 women. You don't. You get 1 woman and it takes 9 months. And some software tasks are non-partitionable. Having a baby is a non-partitional task that takes 9 months. You can't speed it up by getting 9 programmers to do it. It's faster. And there are a number of laws. One another of Brooks' laws is adding more manpower to a late project makes it later. Now, a lot of bosses and things don't understand that. Why is that? Because the people who are working on the project have to train the newcomers and everything slows down. That's a really good book. And then one day, you might have to persuade your boss to program in Erlang. And so you should read How to Win Friends and Influence People by Dale Carnegie. And this is about the psychology of sales, actually, and interacting with people. Very good books. One fun programming exercise is a paper by a guy called D.D. Shorey. You can Google it and you'll find it and download it. Called the Syntax-Oriented Compiler. We invited Dan Ingalls. Dan Ingalls worked with Alan Kay and made the first Smalltalk system. And Dan Ingalls said, "Have you read this paper?" I said, No. Don't read this paper. He said, absolutely don't read this paper. If you do, a month of your life will just vanish like that. So of course I read the paper, and a month of my life just vanished as you implemented the stuff in the paper, and it's seriously good fun. This is the first meta-interpreter that's written in itself, so once it's bootstrapped you can just sort of, This idea of writing stuff in itself it's fun. Your brain will melt as you're doing it. Couple of videos to watch. How are we doing for time? We're doing okay. The Computer Revolution Has Not Happened Yet by Alan Kay. That's a good video to watch. And then just Google Computers for Cynics by Ted Nelson. Yes, and tweet that, everybody. Tweet it so everyone on the planet watches Ted Nelson's videos. I mean, only like 2,000 people have watched the first one, which is absolutely ludicrous because it's good stuff. We'll talk more about this later. Right, so now I'm going to actually get onto some ideas that are forgotten. And well, some of them, there's only 4, so I had to choose. And I wouldn't say they're completely forgotten, but if they are not forgotten, they're not being used. Right. So, and they are in kind of reverse, they get better and better and better. So in fourth place, there's something called flow-based programming. And flow-based programming was invented by John Paul Morrison in the early 1970s. And if you read his book, he says that in the physical world, we create complicated things by placing things next to each other. So, when we build a car, motor, or something, we buy pipes, and we sort of screw them together, and we buy these individual components from different manufacturers, and we connect them together. If you're doing plumbing, you buy these things. You go to the plumber's shop and you say, well, because I don't know what they're called, you say, I want one of these things that connects a funny thing to the thing, and they give you it, and you do it, and it leaks, and you have to call the plumber out to fix it for you. I'm not good at plumbing. But we create programs by, well, that's how we create physical things. We buy these things and we bolt them together. And we don't know how the individual things work. We can do integrated circuits, like in this picture. Let's see if I press the right button. There you go. These are chips, I think. The black things with legs on. And they do magic, because that's hardware. I don't understand hardware. Well, yeah, no. Well, I did quantum mechanics, but it doesn't mean to say you understand how these things work. And you connect these pins together and it just works. And you don't really understand how what's going on inside the thing is. Okay, so flow-based programming just says, so that's all the something called data flow programming. We just connect the inputs of one thing to the outputs of another. And you have another little idea that if errors occur in this chain of things, then forever on we still pass it through the chain, just sort of bypassing it if it's got an error, and we pass it all through. And you have another idea that we'd number everything when we go in. We'd number them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'd pass everything through all the chains. And at the end, we'd sort of collect them all. And then at the end, you would see 1, 2, 3, 4, 5, 6, 7, and you would know if an error had occurred or if it hadn't occurred, and we just connect all this stuff together. And actually, he said that what's in the black boxes should be binary. Shouldn't be able to read it. I thought it was a very good idea, because if you can't read it, you're forced to read the documentation. And this open source stuff, really we should only release binary code and not the source code. And the documentation of how to use the binary code. And then if somebody has to mail us and say, could I look at the source code, please, because I can't understand your documentation, we should hang our heads in shame, because we haven't documented what it should do. The admonition, you go read the code, means, oh, I can't be bothered to write decent documentation. And reading code is very, 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 very difficult. I can't understand, well, I get this urge to rewrite any code that I read, so it's not a good idea. Right. So that was the last slide, that was flow-based programming. And you can think about it. Think about what this principle is. It's got this principle of composability. You can compose things. It's got this principle of black boxness. It hasn't got inbuilt isolation things. The system that does do that. It's got causality. So all these things that I think are good are kind of built into it to a certain extent. What do? We build apps and we build websites. They don't obey any of these principles. We can't connect them together. We can't script them. It's random rubbish. We should be building components that can be wired together. So these are a lot of sins. This is not doing flow-based programming. Sins. Programs we can't remotely control. Programs that cannot share data. Programs that create data in a proprietary format, so that even if they create the data, we can't understand what it means. And programs without a published interface don't do that. Pipes is the second thing. Nobody's forgotten about pipes. You all know about pipes. Hands up who knows about pipes. You mean there are some people sitting here and they haven't stuck their hand up? Okay, now, if you had put your hand up if you know about pipes. They know these sort of Unix pipes. Very good. Keep your hand up if every program you write can be controlled through a pipe. 1. Virtual handshake there. Right. Very good. So pipes. Pipes. For those who don't know, the output of my program should be the input of your program. And in the Unix shell, there's just a little pipe operation. Text flows across the boundaries. So why don't we write programs where the inputs can be piped into the outputs? It's because the bloody GUIs killed it. Programs with GUIs are not pipeable because they are controlled with your little finger going on the bloody GUI. And you can't automate that. And so the invention of the GUI killed the pipe, basically. And people, when they wrote programs with GUI, should have also had an additional interface so they could control the program through a pipe. But they didn't. Right. And pipes were invented by a guy called McIlroy, who wrote this memo to Kernighan and Ritchie. And he said, this was prior to Unix, and he said, we should have some way of coupling programs like a garden hose. Just connect them together and it'll all work. And here's Kernighan and Ritchie, made C in Unix. And they said, yeah, well, you can read that. It's quite good. At that reference, you can find all these papers and Kernighan and Ritchie's comments on these things. Right. And he conceived Unix pipes, which allowed programs to work together with no knowledge of each other. So it's composability. And it's connectability. And it's very nice. So make your programs be remote controlled through pipes. Pipes. Yeah. Yeah. Now, apps, yeah. Horrible things I've mentioned. Oosh. I mean, don't get me wrong, the individual ones are brilliant. My iPad's got some fantastic apps, but I can't script them. I can't make the two work together. They can't share data with each other. And of course, the manufacturers, Apple and people, they don't want you to program these. They've given us supercomputers which we can't program, or make them very difficult to program. Programming is actually more difficult now than it was in the 70s. Picking up programming using BASIC was really easy back in the 70s or 80s. It's really quite difficult now. Right. Linda Tuple spaces. I'll go through this rather rapidly. A Linda Tuple space is a shared whiteboard. Shared whiteboard invented by Violento and Cario in 1986. And it's a kind of more declarative than message passing. I'm into message passing languages. And the trouble with message passing is you need to know who to send the message to. You know, I send you a message, but I need to know who receives the message. So Linda Tuple space is I just write this thing on a whiteboard. Everybody can observe the whiteboard, and anybody can perform the computation and write the answer back on the whiteboard, and I can receive it. So if I'd set up a message passing system, suppose you are a sort of maths machine. I suppose each one of you in the audience can compute, say, a factorial. You know, you know how to compute factorial 10, you know, and if I had a message passing system, I would need some kind of load balancer or scheduler or something, and I need to decide who's not doing any work. You're not doing any work. I'll send you a message. Can you compute factorial 10 for me? And you would do it. Right. In a Linda Tuple space, there'd be a big blackboard, and I would write on the blackboard, please compute factorial 10. And all of you would be watching the blackboard, and you would all race to try and do that, and one of you would win. And that one person would compute the factorial, and they would write the answer back on the blackboard, and I would see it. But I wouldn't know who had done it. And that's the Tuple space. So it worked like this. There are actually 4 operations, but only 2 of them are important, in and out. So out writes something to the shared blackboard, in reads it from the blackboard and removes it from the blackboard. So it's no longer there. Reads it from the blackboard but doesn't remove it from the blackboard. And eval just creates a parallel process. So all you guys, you'd all do an eval to start with. So we're all readers. Yep, we're off, and we're all going. So how would it work? Up here, somebody who wants to compute a factorial. Let's see if I can press the right button this time. There you go. Generate a random integer. That's not completely bulletproof, but it's good enough. Output factorial request with this ID that's a random integer and say, I want factorial 50. That would get written to the blackboard, something like that, with a factorial request, that's the ID. I want to compute factorial 34, 39. And then all the servers, all of them are doing an in request. All of them, they're all doing in at the same time, and they say, I want an input that's a factorial request, that's an ID next. That in will remove that request from the blackboard. Then they'll compute factorial, and then they'll publish it. And this guy will just do an out and then an in. That's it. It's very simple. And that's how simple it is. It's got two primitives in. There's no shared memory, there's no mutexes, there's no locks, there's no futures, there's no promises, there's none of this rubbish. Brilliant stuff. It's lovely. And oh good, I've actually got, I've not run out of time for once. This is good. Okay, so, the next forgotten idea, wait for it, is hypertext. We've forgotten what hypertext is. Or perhaps we never knew what hypertext was. So I'm going to have to remind you, show you a little bit about hypertext. Okay, so here's a little history of hypertext. In 1960, Ted Nelson started work on a project which he calls Xanadu. Xanadu has been called the biggest vaporware project ever. Because nobody has ever implemented Xanadu. The first version of Xanadu came out in 1998. So after, 38 years, an approximation to Xanadu came out. And then in 1962, Douglas Engelbart made a system called NLS, stood for the online system. This was probably the world's first hypertext. It was described as the mother of all systems. It was a hypertext system. It's kind of fun Googling this stuff. If you Google hypertext on Wiki, you'll find references to Engbert's work, and you can go follow these links, you can find little videos of it. And this blew them away. It was an amazing idea. 63, Ted Nelson coins the word hypertext. These guys were doing hypertext before 63, but they didn't know they were doing hypertext because nobody had called it hypertext. They were just making computers with links that you could click on and things like that. Then, 1980, Tim Berners-Lee made a simple hypertext system. So in 1987, there's a 7-year gap. Tim Berners-Lee made the first version of the World Wide Web. And coincidentally, Apple made HyperCard. And actually, it's kind of wrong. I was thinking, hey, anybody could have invented the web, because the web is just like HyperCard where the link is remote. So, but wait a moment, Tim Berners-Lee hadn't seen HyperCard. So he couldn't have connected the idea of HyperCard with networking, because it didn't exist. And then, of course, once people have pointed out this, it becomes kind of obvious. And so Tim Berners-Lee made the World Wide Web, but the World Wide Web is not hypertext. And HTML is not hypertext. And HTML links are not hypertext links, not in the sense that Ted Nelson wanted hypertext to be. So I have to explain a little bit about why this is so, because if you're used to HTML, this might sound funny to you. So the web has got some terrible problems. And I'm telling you about this because I want you to solve these problems. People have been working on it for 38 years and not managed. So, if you're like 20 and you retire when you're 60, you can work on this problem for 40 years and you might make some progress. It's difficult. Okay, so the first problem that the web has got. Right. So this is, do you remember my principle of isolation? My stuff should not break your stuff. So you write this web page, and it refers to something else. And then they change the something else. So they break your stuff by changing their stuff. So it hasn't obeyed the principle of isolation. Page not found. So a hypertext, Ted Nelson's hypertext system, there would be no 401, the links would always work forever and ever and ever. Well, until the sun becomes a red giant, and then it won't work anymore. Unless we found a way to sort of download the entire bloody web to Alpha Centauri or something like that. So, this is the problem. The web is continually breaking because of 401 problems. The next thing, all web pages, these are just sort of random comments, just to sort of lead you into hypertext. All web pages are not writable. And that takes a little bit of thinking about. Right, so let's do a thought experiment. You're reading a web page, and you notice a typo on the web page. And you think, oh, there's a spelling error on that web page. Let's fix it. How do you correct a spelling error when you're in Word or Emacs or something? You just type it. Right. So, if you, now here I have to be very embarrassed. If you go to a well-known website for a well-known programming language, and it tells you if you find a spelling mistake, you've got to do this. So correcting a typo. Well, first of all, you've got to learn Git. And then you've got to locate the program that created the page, and it'll be, somewhere in a database or in a file system, that you'll actually find the spelling mistake if you're fortunate enough to find it. It's a miracle. And then once you've located it, you can correct it if you know. Oh, well, and then you do a push request. And then maybe somebody will go, oh, look, there's some push-pull things. If it's good, and you send a push request to the maintainer of the site. And then after a random time delay, if you're lucky, the typo will be corrected. Isn't that fantastic? How many people make websites? Yeah. And how easy is it if a user of that website noticed there was a typo on a page, how easy is it for them to correct it themselves immediately, instantly? Difficult. How many use this method? All right. Work to do. Here's another method. Select any user, anywhere on the planet, select the text, reverse with your mouse, type in the correction. All people on the planet observing that page will see that change a little bit later. We have to allow for the speed of light. So it won't be instantaneous. It will take the speed of light and a computational delay for that to happen. That's how it should work. That's what would happen if every single web page was writable. Okay, so look at things like the World Wide Web. Well, the World Wide Web, what is it? Links can break. You can't change any page, you can't write any page. What I call sparse knowledge. There's a lot of knowledge there, but it's spread all over the place. It's not all in, it's not difficult. Very few authors make an individual page. And it's gigantic, it's a scan of the, petabytes of data. Okay. If you look at a wiki, in a wiki, links can't break. Well, actually, they can. They'll say this page doesn't create it, you have to create it, but it's sort of. But once you've made them, then they should be there. Wikis have got other problems. You can't rename pages rapidly and things like that. It's anybody can write to a wiki page. And that will increase the quality of the thing. Of course, you have to put in anti-spam things and anti-crowding things and anti-abuse things to stop idiots modifying the page. And you build what I might call a dense knowledge. as opposed to sparse knowledge. And there are many authors per page. Many eyes make light work, they improve the quality. And it's kind of small. The whole, I don't know how big the whole Wikipedia is, it's about 150 megabytes, or last time I looked, maybe up to 800 megabytes or something now. It's dense knowledge. And Ted Nelson said, all there is text. I'm not sure if I'm quoting him correctly. Whoops, he said something like, all there is text, incredibly tangled together. So the more we can tangle it together, the better. Keeping all those links consistent. So that's what we're trying to do, is make up tangled knowledge. Okay, so Xanadu was Ted Nelson's idea of what hypertext should be. And if you look up at this reference, the 17 rules of Xanadu, you'll find that what I've talked about, what I spent like 5 minutes talking about, well, one of them was a third of one of his principles, the other was a complete principle. There are a lot of other principles that govern the reuse of data, the ability to charge for data. You could put into your fragment of data, I allow anybody to reuse it, or I want payment if people reuse it, or they're allowed to modify it, or they're not allowed to modify it. Every user can read and write the net. So there's a long way to go. Can we condense? Could we take web pages and sort of split them into smaller units so we can reason about them? There are better systems than the wiki. And my dear friend Jeremy Rushton made something called the Tiddlywiki. Anybody heard of the Tiddlywiki? Nobody. One person. It's lovely, isn't it? Yeah, great. Tiddlywiki. If everybody in this room, can everybody who's got access to Twitter say, go use the Tiddlywiki, and then Jeremy will wonder what the hell's happened, and he'll be very happy. And an hour spent with the Tiddlywiki was probably better spent than an hour listening to me. Apart from the fact I told you to use the Tiddlywiki, so please do it. Who's going to use the Tiddlywiki after this talk? More hands. More hands. Go on, everybody. You. No, it's great. It's great. It's I wouldn't say it. This is 50 years' experience of programming condensed into use the Tiddlywiki. I mean, it's great stuff. Right. So, I'm retired now. I wander around the world giving lectures occasionally. If it's a nice sunny place, and the food's good, and the company's good. So it's your turn to do this stuff. It's going to take another 30 or 40 years, and I don't expect to be alive in 30 to 40 years' time unless there are major advances in computer science and do precision medicine. Because then, precision medicine's the stuff. Great. Genome analysis and things like that. So fine, I'll just sum up with one thing. When you write programs, oh dear, I've knocked the adapter out. No. When you're giving a talk and you've got your final slide that's don't knock the adapter out, that's really beyond. When you're writing programs, remember this, programs that are not secure and cannot be remotely controlled should not be written. Do not write such programs. And if you write apps, make sure they're scriptable. And if you do write apps, make sure that they are composable. Thank you very much.